so that if you want to go back later on and rewatch me go, like I know a lot of people, it helps them to not just read the notes on their own, but also watch somebody else go through it. So if you do want to rewatch me go through the notes, those will be posted in our class notes videos section of the Google Classroom. So we're into week 2 this week. A lot of you guys already are experts at how to get attendance, which was that first question on Monday. Today, we're jumping into the different states of matter, the solids, liquids, and gases, and the differences in between them, and how we change from one to the other. All right, so we're going to start off with something that sounds very complicated, but is actually a super simple idea. And then we're going to relate that idea to our 3 different states of matter. So is kinetic molecular theory, which is a big, complicated sounding word, which basically just means a theory about how things move. So kinetic is a word meaning how things move around, down at the super, super tiny microscopic molecular level. So the basic idea of the kinetic molecular theory, or sometimes you'll see me abbreviate it as just KMT. The basic idea is that everything in the world, everything in the galaxy, everything in the universe is made up of tiny, constantly moving particles. So all matter, which is a fancy science way of just saying stuff. So the air that you breathe, the fluids in your body, the solids that make up the world around you, it's all matter, and it's all made up of tiny particles that are constantly moving. Now, they might not be moving very much. And when we talk about the solids, we'll talk about how they just move a teeny tiny bit around each other. But all matter, all stuff is made up of these tiny moving particles. So as you increase the temperature of matter, as you make something hotter, it makes the motion of these particles go faster. So the kinetic part comes in here. So the kinetic energy, which is how much energy something has when it's moving, goes up, which means that the particles move faster as the temperature goes up as well. So everything is made out of these super tiny moving particles. And when we increase the temperature, we increase the speed of those particles. We make them move faster and faster. And eventually, if we get them to move fast enough, they'll start to move away from each other. And we'll get to exactly how that happens in a second. So again, kinetic molecular theory, big, fancy sounding word and phrase, but essentially it just means that as we increase the temperature of something, the tiny little particles that make it up will move faster and faster. So what does this mean for our different states of matter? Well, what are the different states of matter? So there are 3 major different states of matter that we're going to talk about tonight. The first one is our solids. So solids you should be pretty familiar with. Most of the stuff that you interact with around you is solid, right? So my computer, the table that it's sitting on, my phone or my mouse, these are all solid, right? Solids have a low kinetic energy, right? So if something is solid, then it's pretty much set in place. So the particles don't really move around a whole lot. They can kind of like vibrate a little bit next to each other and around one another, but that's about it. That's about all the motion that you're getting in a solid. So because the motion is really low, it means that the energy of those particles is pretty low. Some of the major characteristics of solids is that they have what is called a definite shape and volume, meaning that the shape of your solid and how much space it takes up. So volume is just how much space something takes up, is definite, meaning that it is set, right? So it's always going to have the same shape and the same volume, no matter where you put it at, no matter where you move it to, right? My computer mouse right here, it's always going to be this sort of ovally shape, and it's always going to take up this same amount of space, no matter if I'm holding it in my hand, or if I put it on the table, or if I throw it out the window of my room. It's always going to be the same shape and the same size. So that's kind of the characteristic of a solid. No matter where you move it to, no matter what kind of container that you put it in, it'll always have the same shape and size. So like in our little picture here, we've got this little cube of these little particles that are stuck together. Again, not a lot of movement. They're pretty set in place. And we could take this cube out of this vase, out of this container, and put it somewhere else, and it would still be the same shape and the same volume. So always is going to be the same when it comes to what size that it is and how much space that it takes up. Up next, if we add a little bit of energy into our matter, we might get it to turn into a liquid. The liquids have a little bit higher energy than solids, right? If you think about liquids, they're a little bit more fluid. You can move around easier. So the particles in a liquid are able, instead of being all like stuck together, they can kind of move around each other a little bit. All right, they're not totally separate apart from one another. They're still kind of close, but they can pretty easily move around each other. So because there's more movement, there is more energy. They have a higher energy in liquids than we do in solids. Liquids have an indefinite shape. You can't have a set shape of water, right? Water doesn't come in a shape. It'll take the form of a specific shape if you pour it into a square-shaped Tupperware or a circular bowl or a tall, skinny glass. It'll take up the shape of that container, right? But it doesn't have a shape on its own. So that's what we mean by indefinite shape, right? There's no set shape to liquids. They just kind of fill up whatever container that you put them in. So the type of container that they're in, that will determine the shape of the liquid. It doesn't have a specific shape on its own. Unlike this pen, for example, which will have the same pen shape no matter where I put it, liquids don't do that. They take up the shape of their container. But they still have a definite volume, right? If you take a pitcher, if you take a cup of water and you pour it into a pot, and then you pour the water from that pot into a bowl, and then you pour the water from that bowl into a drinking glass, and then you pour the water from that drinking glass into the measuring cup, it'll still be 1 cup of water, right? So liquids have a definite or a set volume, all right? Their volume doesn't get bigger or smaller all on its own, right? You have to add in extra liquid in order to get it there. So while they take up any shape that their container is in, liquids keep the same volume, the same amount of space that they take up. So there'll always be a set amount of their volume. So in our liquidy here, again, before we had that tight block of particles. Now all the particles are a little bit more spaced out. They're a little bit further apart from each other. They're moving around a lot more easily. That's why when you like shake a glass of water, you can see it get all moving around and sloshing around each other. That's because those particles are further apart, moving around all around by each other. So higher energy in liquids, they don't have a set shape, but they do have a set volume. All right. And then finally, our third and final state of matter that we're going to cover this evening are our gases. So gases, the last state of matter, you don't normally think about gases a whole lot, since for the most part, they're invisible to us. We can't really see gas moving around our head, but it is always around us. This is what we have to breathe in order to stay alive. Out of the three different states, gases have the highest kinetic energy. So the particles in a gas can move and separate and fly around really fast all around one another. All right, so instead of being sort of stuck together like in a liquid, in gases, the particles are totally separate from each other and zooming all around wherever you put them. So we have much higher energy in gases compared to our liquids or our solids. Gases both have an indefinite shape and an indefinite volume. So what this means is that they, like liquids, they will take the shape of the container that they're in, and they will expand and contract their volume to fit that container, right? If I had like a glass or like a screw top can, like a water bottle, right? And I kind of zoomed it all around me and then put the lid on, the inside of that water bottle is full of gas, right? That's why it doesn't get all collapsed, because there's gas on the inside of the empty bottle. And that gas is taking up the whole space of the bottle, right? There's not going to be pockets. It's not like a liquid where it just fills up at the bottom and that's it. Gases will spread up and take up the whole space of whatever container that they are put in. So that's why they do not have a set shape and they don't have a definite volume. Whatever size container that you have, that's how much gas you have in that container, right? Because the particles are so spread out, so separated and zooming all around really fast, they just fill up whatever container that they are in. So really high energy particles are zooming around, moving super fast, spreading out throughout the entire container. So they do not have a set shape and they do not have a set volume for our gases. They just expand and take up room and fit each container that you put them in. All right. Any questions so far about our solids, our liquids, or our gases? Feel free to either share out loud or put it in the chat if you do have a question. All right, doesn't sound like anybody has any questions right now, but if you do think of one write it down or feel free to ask me about it at the end of the class today, and I'll do my best to answer. So just a quick review. Solids, lowest amount of energy, particles, super tight together. Actually, hold on, I can probably back. The start of solids, low energy, particles close, stuck to each other, not a lot of movement going on. And they have a set shape and volume that will always be the same. Liquids have a little bit higher energy, so they have kind of the middle amount of energy. The particles aren't completely separated, but they do move and flow around each other a lot more than in solids. Liquids still have a set volume, right? A cup of water is a cup of water, no matter where you put it, but they do not have a set shape. They have an indefinite shape. Their shape will be whatever sort of container that you put them in. And then finally, gases. These guys have the highest amount of energy, so their particles are moving super fast. They're zooming all around each other, and they do not have a set shape or volume. Because those particles are moving so fast and they're so far apart, they'll take up whatever space and whatever size container that they put them in. Yeah, Breeze, if you want to come back later on and watch the video of me going through it, or if you're able to join back in before we leave, that is totally fine by me. All right, so the next thing that we're going to talk about, we've gone over our states of matter, but states of matter don't stay that way for their entire existence. Solids are not always going to be solid. Liquids may not always be liquid, and gases might not stay a gas forever. Instead, it's possible for them to change from one state to another. So we call these changes phase changes. So when we go from a solid to a liquid, or from a liquid to a gas, we call it a phase change. We're changing from one state or one phase to another. So a lot of these you guys have probably heard of before. So I'm going to ask for your help a little bit. So what is it called when we go from a solid to a liquid?
Melting.
Melting.
KMT.
Bingo.
KMT.
Solid to liquid's melting. Solid to gas is evaporation, or liquid to anything to gas is evaporation. From gas to liquid is condensation. And the temperature drops.
Good job. Yes, that's the answer. I'm just
Yeah. Awesome. So yes, Jonathan nailed it on its head, but just to go through a little bit slower than he did. So solid to liquid is melting, right? We take something that is solid, we heat it up to a certain temperature, and then it starts to melt to a liquid, right? That's why if you take a piece of ice and you leave it out on your counter for several minutes, you're going to come back to a puddle of liquid water. And that's due to the ice melting. It got too warm to stay as a solid. Its particles started moving around too fast, so it phase changed into a liquid. One that I don't think I heard Jonathan mention was, what about if we go from a liquid back into a solid? What is that called?
Evaporation. I don't know.
Close, but not quite. That's actually a different one that we'll talk about in a second. So we have liquid water. How do we turn it back to solid ice?
So I meet this challenge in that way. I show the show. She'll carry you. I
I have it.
So what do you got to do to water if you want to turn it into ice cubes?
You can freeze it.
Freezing. That's it. Freezing is another phase change, which is the opposite of melting. So in melting, we're going from solid to liquid. When we freeze, we go from liquid to solid. So we cool something down to the point where the particles get really tight and start to really lose some of their energy. And when that happens, it forms up into a solid. So yeah, exactly like Annette mentioned, if we want to take some ice cubes, if we take some ice cubes and leave them out on the counter, they're going to turn to water. But if we take that water and scoop it back into the ice tray and stick them back in the freezer, then they're going to turn back into solid ice. So the temperature that this happens at is called the melting point, but it could also be called the freezing point. So there's a specific temperature for every single piece of matter that is out there, where if it gets hotter than that temperature, it'll start to melt and turn into a liquid. Or if it gets colder than that temperature, it'll start to freeze and turn into a solid. So does anybody know in either Fahrenheit or Celsius what the melting or freezing point of water is?
-1.
Close, but not quite. Very close though. Anybody else happen to have any guesses on what the freezing or melting point of water is?
32 degrees Fahrenheit.
32 degrees Fahrenheit. Bingo. So in Fahrenheit, the freezing and melting point is 32 degrees. And Celsius, it is 0 degrees. Both of them mean the same thing. So at 32 degrees Fahrenheit, solid ice blocks will start melting into liquid water. Or if we have some liquid water, if we cool it down to 32 degrees Fahrenheit, it'll start turning into solid ice blocks. So depending on if we're a liquid going to a solid or a solid going to a liquid, it melts and freezes at the same temperature. So that's kind of the changing point of going from one to the other. So there are a couple other phase changes since we don't just have solids and liquids out there. We also have going from liquid to gas. So there's actually a couple different ways that we can change from liquid to gas. One of them is called vaporization, which is also commonly known as boiling. So you're getting ready to make some pasta. You stick a bunch of water on the stove and crank up the heat. And after 7 or 8 minutes, you start to see all those bubbles start to form and come up, and you see all the steam coming off the top of the pot. That's due to vaporization or boiling. So our liquid is getting so hot that it is turning to gas. So the liquid water in your pot is turning into water vapor, which is a gas that's coming out and going up into your kitchen. So that's one way that we can go from liquid to gas. It happens really fast. This is a really quick way of boiling off water, causing it to change to water vapor, is this vaporization. But that's not the only way to get from a liquid to a gas. So you probably noticed at some point in your life that after a big rainstorm, right, there might be some big puddles on the side of the road or on the sidewalk that you have to walk on. And by the end of the day or a day or two later, those puddles are gone. Now, all the water in those puddles did not go away because it got boiled away. If it's ever at the boiling point of water is like 212 degrees Fahrenheit. So if it's ever that point outside, then something has gone terribly wrong on planet Earth. Instead, what they did, and something that Jonathan pointed out earlier, it evaporated. So even when we're not at the boiling point, liquid can still change to gas, kind of all on its own, but it's a much slower process. So vaporization and evaporation are the same overall process of changing liquid to gas. It's just vaporization is where we have it happening extremely fast, extremely quickly at what's called the boiling point. And evaporation is where it happens all on its own, but it happens much more slowly. So it can happen below the boiling point. It doesn't have to be super hot. The liquid will kind of naturally turn into a gas. But it's a much slower process. So it'll happen over a pretty long period of time. Finally, if we want to go from gas that's kind of zooming around, floating in the air, back down to a liquid, then we have condensation. So condensation is what happens when we have a gas and we cool it down enough to become a liquid. So condensation is the reason why we have rain. So there is a good amount of water vapor up in our atmosphere, kind of floating around as a gas. Eventually, due to different weather pattern, that water vapor will cool down a little bit and kind of start to clump together in big pools of water in the sky, which we call them clouds. So clouds are just a whole bunch of water vapor that's kind of started to stuck together. Eventually, if we get a whole bunch of clouds together and that water vapor starts to really cool down, the water vapor in the atmosphere changes to liquid water because it gets cool enough. And due to condensation, it falls out of the atmosphere as rain. This is also the same thing that happens when you have like a really cold glass that you either just got out of the fridge, or you have that like a plastic cup from like Whataburger or McDonald's or something, and it's full of ice, so the inside is really cold, and the outside, after a couple minutes, you can start feeling that condensation on the outside of your glass. And that's because the glass is getting cold, or the plastic is getting cold because of all the ice and liquid that's cold on the inside. And so it's actually cooling down the water vapor and the air around it enough to where it's forming little tiny droplets on the outside of your glass. So the reason why your grandma wants you to put a coaster down before you put your glass on her wood countertop or her wood coffee table is due to that condensation of water appearing on the outside of a cup. It's not because it's leaking out of the cup or because you spilled water on the outside. It's because the cold air, the cold water inside the cup is causing the air on the outside to cool down and stick to the cup as little droplets. So we can go from liquid to gas through either vaporization or evaporation. And then we can go from gas back down to liquid through condensation. So those are actually kind of all the main ones that people are most used to and most familiar with. But there's actually one more set of phase changes that we're going to talk about. So we've talked about changing between gases, or between solids and liquids and back to solids. We've talked about changing from liquids to gases and back to liquids. But the last thing we're going to talk about is changing directly from solids to gases and then back down to solids. So these two processes are called sublimation and deposition. So sublimation is what happens when we have a solid and it gets so hot that it skips the liquid step entirely and immediately starts turning into a gas. So I don't know if you've ever seen dry ice before. Sometimes people will use it for parties and barbecues and stuff like that. Dry ice is not actually water-based ice. It is frozen carbon dioxide gas. So they take this carbon dioxide, they freeze it down really, really fast. It turns into these big blocks that people call dry ice. Because when you take these blocks out of the super cold freezer, the blocks are extremely cold. And so the air, even though to us it might feel like a pleasant 70, 75 degrees, to the blocks that is scorching hot. So they start immediately just giving off gas. So dry ice looks really cool because it starts to give off like kind of this spooky gas effect whenever you open the cooler. But what's happening is called sublimation. We're going straight from a solid to a gas. The flip side of this is deposition, which is, like I just mentioned earlier, we take some gas and we freeze it down really, really fast. It skips over the liquid step entirely and goes directly to the solid step. Yeah, Annette mentioned that dry ice is great for Halloween and haunted houses type stuff. And yeah, it's because it gives off this kind of like spooky cloud atmospheric effect because it is going directly from the solid form to turning into a gas and kind of emanating out from its container. So here is a handy little chart that I found that kind of puts everything all together for you guys in one place. So we have our solid particles, our liquid particles, and our gas particles. And if you want to know the name of how to get from one to another, you just follow the arrows. So to go from a solid to a liquid, we go through the process of melting. And then to go from a liquid to a gas, we go through the process of evaporation or boiling, also called vaporization. If we go from a gas to a liquid, it is condensing or condensation. And if we go from a liquid to a solid, we go through the process of freezing. And then finally, if we go through one of those kind of weird ones, we can go directly from a solid to a gas through the process of sublimation or by subliming. And we can go from a gas and freeze it directly down into a solid through the process of deposition. So for your homework and for your upcoming, well, not super soon, but for upcoming quizzes or exams, it'll be important for you guys to know the names of these changes. So melting, evaporating and vaporizing or boiling, condensing, freezing, sublimation, and deposition. Any questions on the phase changes, what's going on, or what they are called?
Will you give us notes on like what is what to prepare us and let it write in like a notebook or something?
Yeah, I mean, you're always welcome to write down anything that you want. Also, since we're still doing online school for the near future, you can always go back and relook at the notes whenever you need to. All right, so the quizzes or the tests that we do in this class aren't timed and they're not, you're free to go back and look at these notes whenever you need a refresher on something.
Wow, thank you.
All right, no problem. Any other phase change related questions? All right, so as I mentioned, the homework for this particular set of the notes is pretty straightforward. Some of you have already worked on it a little bit, which is totally fine. Remember, if you want to go back and change some of your answers after tonight's class, you're more than welcome to. And so both versions of the homework have this little initial kind of reminder part of some of the differences between solids, liquids, and gases. And so for the first part of the homework, all you have to do is label these diagrams as being either a diagram of a gas, a liquid, or a solid. And then we have another little reminder section about the different names of the phase changes. And then we have a little triangle diagram down here where each one of these arrows has a label on it that is numbered and that corresponds to one of the phase changes that we talked about tonight. And so all you have to do is go through and label what phase change each arrow is referring to. So there's 6 phase changes, and so therefore there are 6 arrows to label. So that is it for the homework for tonight. Here's what the Google Doc version looks like. It's all the same material. It's just presented a little bit differently. So on this one, you can actually, if you want to, go ahead and directly label the different diagrams as solids, liquids, or gases. But then we have the same thing right here. So for each number that goes along with one of these arrows, you'll write down which phase change that it describes. All right, any questions about the Tuesday assignment?
The pictures on the top, do we have to label them, you said?
Yeah. So either on the Google Doc version, you can write the labels directly underneath the pictures. So right on the lines right here, you can type in if it is a liquid, a solid, or a gas. And then on the Google Form version, there's the pictures. And then down here, you just have to pick which phase or which state matches the left picture, the middle picture, and the right picture.
Okay, I turned mine in, today in the morning, but I'm not sure if I did that correctly. I'll have to double check.
That's okay, yeah. If you want to double check, and if you did mess it up the first time, you can always resubmit it, and I'll look at your whatever your most recent submission is.
Okay, thank you so much.
Yeah, no problem. Yeah, so when you're going through, make sure that you're doing those 2 parts. So you're labeling the diagrams and you're labeling the arrows. All right, good question. Any final questions about the Tuesday assignment?
No, this is Larissa. I've been in here for a little bit. Like I got in here like at 5:45. I see that it's recorded, this class. I can always just go back and look at what I've missed, right?
Yep, exactly.
Okay. Just wanted to make sure.
For sure. No worries. Good to see you, Larissa. All right. So the next thing that we're going to go, so that was a pretty short set of notes about just the solids, liquids, and the gases. And so I wanted to add on an extra thing that kind of takes it to the next level a little bit. And that is the idea of a heating curve. So heating curves are also sometimes referred to as phase change curves or phase change diagrams. And essentially, a heating curve is a graph that shows the temperature of a piece of matter, whatever it is that we're measuring, whatever stuff that we're doing our measurements, our observations on. It shows the temperature of the matter as heat is added to it over time. So kind of the most common example I think of is if you take a big ice block and stick it on the stove and then turn the stove on low, the heating curve would show as time goes on, what is the temperature in either that ice block or eventually that water or that water vapor as it gets more and more and more heat added to it. So a heating curve looks something like this. And don't freak out yet. I promise we'll go over what all of these random looking descriptions mean. But for now, just focus on the shape of the curve. So we have our temperature over here on the y-axis, which is the up and down part of the graph. And we have our time down here on the x-axis. So as we move towards the right, it means that the time is going on longer and longer and longer. And so if you see, the shape of a heating curve generally has these characteristics, where it starts off at some point, and then it starts to get warmer for a little bit, and then the temperature stops going up, and then it gets even warmer for a little bit, and then the temperature stops going up again for a little while, and then at the very end, it starts to get warmer once again. So as our line gets higher and higher, that means that our matter is getting warmer. So the main thing, or I should say the main two things that we're going to focus on tonight is what's happening in these parts where we're getting warmer and warmer, and why do we have these flat sections on our curve? Even though it's on the stove, why does our matter stop getting hotter for a certain period of time? So that's kind of what we'll go over today. So the first thing that I want to mention before we actually jump into the heating curve itself is the idea of kinetic energy and potential energy. So kinetic energy, we actually already talked about a little bit. Can anybody remind me what the word kinetic means or what it refers to?
Energy. An object is moving.
Yeah, motion, exactly. So kinetic energy has to do with motion. And that's the one that we already talked about a little bit earlier with that molecular theory, that KMT. So kinetic energy is all about how fast that the particles are moving. So we said that our solids have low energy. They have very slow, stuck together particles. Our liquids have medium kinetic energy. Their particles move around a little bit more. And then our gases have high kinetic energy. We have a lot of particle motion in our gases. And we also mentioned that as we increase the temperature of our matter, it makes the motion of our particles go up. And so when motion goes up, that means that our kinetic energy is going up. So as the temperature goes up, our particles move around faster, which means that our kinetic energy is going up as well. So that's kind of a little bit more straightforward one to talk about. We already talked about it a little bit earlier. So that is what is happening on these points of the heating curve where our line is going up. So like I said, imagine we're taking a big block of ice and sticking it on the stove. That block starts off as a solid, and then as the stove gets turned on, that ice is going to start to heat up. So we're staying as a solid, but the kinetic energy of the ice is starting to go up because the temperature of the ice is starting to go up. Same thing with this big section in the middle here. Now our matter has changed to a liquid. And so we start off with freezing cold water, but it's on the stove, so that water is getting hotter and hotter and hotter and hotter. So the kinetic energy of our water is going up. Water gets hotter, kinetic energy goes up. So we start off with a super duper cold liquid, and we end up with a super hot liquid. And then finally, eventually, our liquid will turn into gas. And so the gas will then start to be heated up by the stove as well. So that's why we have this ending point that starts to go up, because our gas starts to increase in temperature as well. So we start off as a solid with the temperature going up. Eventually, we become a liquid that gets hotter and hotter. And then eventually, we become a gas that starts to get hotter as well. So that's what these kind of vertical lines on our graph means. When the line goes up, that means that we are in a particular state of matter. We're either a solid, a liquid, or a gas, and the temperature of that state is going up. Any questions so far about kinetic energy or why we have these lines going up on the heating curve? All right, I know this is something that, don't worry about if you're finding it a little tricky so far. This is something that everybody finds a little bit tricky. So if you ever do have a question, please know that there's probably at least 2 or 3 of your classmates that have the same question. So please do not be afraid to either ask it out loud or write it down in the chat so that I can make sure to get it answered and to get everybody on the same page. So our lines are going up because we have a state of matter that is getting hotter. But what about these flat lines right here? If our ice block is on the stove, why isn't it just a straight line from being super cold to being super hot? So the reason for that has to do with an idea called potential energy. So it's related to kinetic energy, but it is a little bit different. So whereas kinetic energy refers to how fast the particles are moving, potential energy refers to how close the particles are together. So how close, how tightly those particles are fused together, that is their potential energy. So the more space that particles have between each other, the more potential energy is in your matter. So solids have a really low potential energy because their particles are really close and stuck together. Liquids have a higher potential energy because their particles are able to move around each other a little bit. And gases have the highest potential energy because their particles are super far spread apart. So, in order to increase the potential energy of matter, we have to change its phase. We have to go from one phase to another. So this was that melting, that evaporating, that sublimating that we talked about. All of that is changing the potential energy of our matter. And so as matter changes phase from either solid to liquid or liquid to gas, the potential energy of that matter is going up because the particles are getting more spaced apart, more further apart. So going from one state to another is causing the potential energy to go up because we're spreading those particles away from each other. And being further away means they have more potential energy. Now, the tricky thing about potential energy is that as we are spreading these particles apart from each other, that's taking a lot of the energy from the heat. So a lot of our stove's energy is going into spreading out these particles during this phase change. What that means, though, is that as the particles are being forced to spread out, they're not speeding up and moving faster quite yet. So because they're not speeding up, that means that our kinetic energy is not changing, which means that our temperature is not changing either. Our temperature is staying the same. So when we have these phase changes between matter, so when we're going from a solid to a liquid or from a liquid to a gas, we're putting all of our energy into breaking apart and spacing out these particles, and none of it is going into actually making them faster or hotter. So that's why, as these phase changes are going on, we have those flat lines on our heating curves. So you may remember from about 20 minutes ago, we said that changing from a solid to a liquid is called melting. So the reason why we have this flat line on our heating curve here is that as our ice block is changing from a solid to a liquid, its temperature is staying the same. And for water, which is the example that we're working with here, water melts at a temperature of 0 degrees Celsius. So in science, we like to use the metric system for reasons that I'll talk about later on in this term. And in the metric system, we use Celsius for temperature and water melts at 0 degrees Celsius. So we start off with this really cold block of ice. We get it warmer and warmer and warmer as a solid piece of ice, but then it hits 0 degrees and it starts to melt. And when it starts to melt, we stop getting hotter. So while the melting process is going on, the temperature is staying the same. It's not going up. Eventually, we melt all that ice, and now all we have in our pot is water. So we talked about earlier about how now our liquid water is going to get hotter and hotter and hotter. We're going to have that kinetic energy go way up until we hit our boiling point. And in water, the boiling point of water is 100 degrees Celsius. So as soon as water hits 100 degrees Celsius, that's when you'll start to see those little bubbles forming in your pot. And as long as the water is boiling, it's going to be staying at 100 degrees Celsius. So the temperature doesn't go up because we're not making our particles move any faster, but the potential energy is going up because we're spreading apart those particles and turning them into gas. So we're boiling, also known as vaporizing, and we're turning our liquid water into gas, water vapor. But while this boiling process is going on, the temperature is staying the same. It's not going up. That's why we get this second big flat line on our heating curve. No temperature increase because of the boiling that's going on. Eventually, all of that water boils away. And so now any of the gas that is still hanging around near your stove is going to start to heat up due to absorbing all that energy coming off of the hot stove. So when we're going through our phase changes, we're splitting apart our particles. The potential energy is going up, but we have these flat lines because the temperature is staying the same. The temperature does not go up when we are changing from one phase to another. All right, so this is a little bit trickier part of the heating curve process. So does anybody have any questions about the potential energy, the flat lines, the melting and boiling? Any questions on this part of the heating curve?
No, sir. Thank you.
No problem, Cameron. Anybody else? And remember, if you do have a question, there's probably at least one or two other people who are thinking the same thing. So anything about this potential energy boiling stuff that you guys want me to go over again? All righty. So before we wrap up, I just wanted to put all of the different parts of the heating curve all together and kind of talk you through what's going on from start to end. So we start off down here as our super cold block of ice. We stick that on the stove. We turn on the heat a little bit, and our super cold ice is going to start to heat up. So we have a thermometer that we have stuck right into the middle of the ice, and we can see that it's going from really cold, -20 degrees, and it's creeping up and up and up. Finally, that ice hits its melting point, which for water is 0 degrees Celsius. So now we start off with our solid ice, but when we hit that melting point, we start to melt and turn into a liquid. But while we're melting, our temperature stops going up. our temperature stays the same because the particles aren't moving faster, they're moving away from each other. So the kinetic energy isn't changing here, but the potential energy is going up. So we start with a big block of ice. It's melting, 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 until finally it becomes liquid water. So once all the ice has changed into water, that is when we start heating up again. So our liquid is getting hotter and hotter. It's going from 0 degrees Celsius and going warmer and warmer, 20, 40, 60, 80. So we're getting warmer, which means our kinetic energy is going up because our particles are moving faster and faster and faster. Eventually, that water will get so hot that we will hit our boiling point, which in the case of water is 100 degrees Celsius. So once our liquid hits that 100 degrees Celsius mark, it's going to start boiling or vaporizing. So again, our particles are moving away from each other, but not moving faster. So the potential energy is going up because we're getting further and further apart as we turn into a gas, but the temperature is staying the same. So if you stick a thermometer into boiling water, whether or not it has just started to boil or it's been boiling for 5 or 6 minutes, it's still going to be 100 degrees Celsius. Eventually, after a long time of boiling, we boil all the water away. We turn it all into gas vapor. And then, finally, our water vapor, which is a gas, will start to heat up. So now our particles are fully spread apart. And if we leave the heat on the stove, the gas around the stove is going to get hotter and hotter and have its particles move faster and faster. So that is how we read a heating curve. We start as a solid. We start to warm up and heat up in temperature until we melt, at which point we change from a solid to a liquid at the same temperature. That liquid then starts to heat up and get hotter and hotter until it starts to boil. And then while we're boiling and going from a liquid to a gas, we are staying at the same temperature. And finally, once we've all changed to gas, the temperature of that gas will start going up. Any final heating curve related questions? Anything about the process that I just went through that you're still a little bit confused or a little bit not quite sure about? All righty. So for tomorrow's homework, tomorrow's assignment that'll be posted tomorrow morning, we have a heating curve that looks pretty similar to the one that we were just looking at. Only now, instead of having all of those labels, we just have these letters kind of marking these different points on the curve. And so essentially all you have to do is there is a series of questions that basically ask what's happening at this point in the heating curve, or what state are we in between this letter and this letter. And so this is a heating curve of water. So there are a couple questions that ask about temperatures where stuff happens. And so it's relating to the temperatures of water. And so it's only by, I think, six or seven questions that just ask about what is going on with our matter, with our water at these different points on the heating curve. So hopefully pretty straightforward. Although I know last term when we went through this, I had a lot of people that struggled with this one a little bit. So please remember, you can always reach out to me on email or text message or on the Google Classroom. If you're ever feeling stuck and you want some help or you need me to run through a little bit of the heating curve with you again. But again, that is the daily assignment that'll be going up on Wednesday. So make sure to check that out tomorrow to get your Wednesday attendance credit. All
Thank you
righty,
for
guys.
today.
Okay, thank you.
Have a good night.
So anybody have any final questions about the states of matter, the heating curve, or any of the homeworks?
No, sir.
Uh,
Thank you. You have a good night.
I have
I
a
think
question.
I
Yeah,
got
go
it
for it,
down,
Douglas.
but I think I'm gonna watch the video again just to be sure.
Yep, that's totally fine.
Those
Yeah, Douglas, you
I
have a
saw
question?
yeah, the assignment that I saw today was like those little circles. That's like when they're all together, that's solid, and when they're like little bit of circles, that's a liquid, and when it's just like the two circles, it's just like that's gas, right?
So those circles represent the particles
Atoms.
of the matter. And so I can't 100% tell you directly, but yeah, so remember that solid is when the particles are the most compact and the most fused together. And then liquid is when the particles have a little bit more movement and are a little bit further out. And then the gas is when the particles are completely spread out and far apart from each other.
Okay, thank you.
No problem. Good question. All
So,
right.
this is Larissa. I have a question.
Yeah, go for it, Larissa.
So, the work for tomorrow is on heating curves, right? The little quiz tomorrow. That's
Yep.
okay. Just want to make sure. Thank you.
Mm-hmm. Exactly. Yeah. So the daily assignment that went up today was about the solids, liquids, and gases and the phase changes. So like the melting and the boiling and stuff like that. And the condensation and fun stuff. And then, yeah, the daily assignment that goes up tomorrow will be about the heating curve.